going to have a look at 7.3. Knowing some common oxidizing and reducing agent. The first one that we're going to look at is the one you saw in the video, potassium manganate, 高锰酸钾. Don't forget to put the oxidation state of manganese ion. It's 7. The chemical formula is KMnO4. Like any ionic compound, the naming follows the positive ion followed by the negative ion. In this case, the negative ion is a polyatomic ion, MnO4-. If we calculate the oxidation state of manganese, for oxygen, the oxidation state is -2, and overall it has a minus charge. So manganese has a +7 oxidation state, which is really, really positive. It has a really strong tendency to gain electron because it's so positive and it's not very stable. And after gaining some electrons, manganate ion will be reduced to manganese 2 ion, and it's followed by a color change. The MnO4- ion is purple and the manganese 2 ion is colorless. If you see a color change from purple to colorless, that means manganate 7 ion has gained electrons, and gaining electron is called reduction. So who causes manganate ion to gain electrons? It must be a reducing agent who's able to donate electrons to manganate ion. So this is a test for the presence of a reducing agent. Okay. In the video, we could see a titration experiment. In a titration experiment, there's a very thin equipment with a tap. This is called a burette. And in the burette, it's filled with acidified potassium manganate. And the color of the solution is purple. In the conical flask, they've prepared some solution with iron 2 ion. And this iron 2 ion is acting as a reducing agent. It is able to lose one more electron, so that going from carrying 2 positive charge, it's going to be even more positive than before. It loses 1 electron to do that. And where does the electron go? It goes to the manganate ion. So that's why in that video, we could see as the purple droplets come in, immediately as it reacts with Fe2+, it becomes colorless. So when does it stop? When all the Fe2+ ion are turned into Fe3+ ion, then there's no reaction happening. That's why when this purple droplet comes in, without anything to react with it, there will be a permanent pink color in the conical flask. Right, you will see a worked example on page 13. So I'm not going to go to too much detail. Moving on to the half equation, since we have talked about the oxidation reaction, losing electrons, let's have a look at of the reduction reaction, gaining electrons. So how to balance such equation? It's very complicated. In this equation, we have the oxidizing agent who can take electrons from others. We also have a hydrogen ion. So what is the role of the hydrogen ion over here? It's acting as an acid. In order for the redox reaction to take place, this has to take place in an acidic environment, and the acid is provided by hydrogen ions. So to balance this equation, firstly, we need to find out the number of electrons transferred. Step 1. Find the number of electrons transferred. You can work this out by using the oxidation state change. Going from +7 to +2, every Mn has gained 5 electrons, which is done for you. But we haven't balanced the charge yet. So step number 2, you need to balance the charge. Using your proton, using the hydrogen ion. On the right hand side, we have 2 positive ions. We have 2 positive charges. On the left hand side, we have 6 negative charges. How many positive charges do I need to put to get an overall of 2 positive charges? The answer should be 8. 8 positive plus 6 negative. Overall is 2 positive. So we've successfully balanced the charge using hydrogen ion. Lastly, we haven't balanced the hydrogen and the oxygen yet. We need to use water molecule to balance hydrogen and oxygen, then everything's balanced. In this equation, we have 8 hydrogens and 4 oxygens on the left hand side. So we can simply put 4 in front of H2O to balance the whole thing. Moving on, let's have a look at the second common oxidizing agent. Potassium dichromate. The oxidation state again is very high. The oxidation state is +6. K2 Cr2O7. Why K2? Because dichromate ion has an overall charge of 2-, but each potassium ion has a charge of +1. So we need 2 positive charges to cancel out the 2- charges. As you can see, most of the good oxidizing agent has a very high oxidation state, and that's why it has a tendency of gaining electrons. After gaining electrons, after being reduced, it goes from +6 to +7. So each CR should gain 3 electrons from others. It's able to grab 3 electrons from others. It's a good oxidizing agent. Again, it's followed by a color change. When it's dichromate 6 ion, it's orange. This is orange. But when it's reduced to chromium 3 ion, it turns to green. Again, this is a test for the presence of a reducing agent, just like in the previous example. If there's a reducing agent, somebody can donate the electron to dichromate ion. Moving on, we have a very similar problem over here. So you can pause the video for a second to think about how to balance the half equation using the same steps. Let's balance the chemical equations together. In this half equation, we have 2 chromium. Chromium on the left hand side, but only 1 on the right hand side. So firstly, I need to make sure I have 2 chromium 3 ions on the right hand side. Then, because each chromium can gain 3 electrons, 2 chromium should gain 6 electrons. I've calculated the number of electrons transferred. I need to move on to step 2, balancing the charge using hydrogen ion. On the right hand side, I have 3 positive charges. On the left hand side, in order to have 3 positive charges overall, I need to have 14 hydrogen ions to give an overall charge, to give an overall charge of 6 plus, not 3 plus, 6 plus. Lastly, I need to balance the number of oxygen and hydrogen using the coefficient in front of water molecule, and this should be 7. Moving on to the last oxidizing agent, potassium iodide, Ki. Sorry, this is not an oxidizing agent, this is a reducing agent. Why is it a good reducing agent? As we saw in the previous lesson, an iodide ion does not hold on to the electron very well. It can easily give away the electron to somebody else. So it will be oxidized to I2. And the half equation is 2 iodide ions kick away the 2 electrons and become iodine. By kicking away the electron, it's oxidized, and this guy will add the electrons to somebody else. So that's why it's a reducing agent. It's good at reducing others. And this is a test for the presence of an oxidizing agent. The person who gains that electron is the oxidizing agent. That guy is the one who oxidizes the iodide ion. Let's have a look at this particular reaction where hydrogen peroxide reacts with potassium iodide. In this case, potassium iodide is a reducing agent. The oxidation state goes from -1 to 0. As you can see, the oxidation state has increased. It's oxidized. And from this, we can see each iodide ion has lost 1 electron. And moving on, who's getting reduced then? It has to be hydrogen peroxide. If we work out the oxidation state of oxygen here, it's a bit interesting. In this case, hydrogen is still +1, but oxygen, instead of being -2 in most cases, is -1. Moving on to the product side, oxygen is -2. Going from -1 to -2, the oxidation number dropped. That means it's reduced. Because the oxidation number dropped from -1 to -2, that means each oxygen has gained 1 electron to go from carrying 1 minus charge to carrying 2 minus charges. Lastly, let's talk about sulfuric acid. What is the role of sulfuric acid over here? We can see there's no change in SO4 before and after. It's basically a spectator ion, and the oxidation state of hydrogen hasn't changed before and after. In this reaction, the hydrogen ion is only acting as an acid. This redox reaction takes place in an acidic environment, just like in the previous 2 examples. Again, let's balance the chemical equations that involves hydrogen ion. In an acidic environment, let's look at how hydrogen peroxide is acting as an oxidizing agent by getting reduced itself. First of all, we can find out the number of electrons transferred by balancing the number of oxygens. On the left-hand side, we have 2 oxygens, but we only have 1 on the right-hand side. You need to put 2 in front of H2O. Don't worry about hydrogen. Later on, we can always balance the hydrogen using the hydrogen ion over here. And by looking at the oxygen state, because each oxygen involves 1 electron transfer, and we have 2 oxygens. So here, 2 electrons are gained, 1 to each oxygen. Lastly, balancing the charges. We have no charge on the right-hand side. To balance out, to neutralize the charge, we need 2 hydrogen ions over here. Sometimes, for simplicity, we don't call it hydrogen ion. We can also refer to this as a proton, because think about it, a hydrogen atom is carrying 1 proton and no neutron, and 1 electron. If you remove 1 electron from this hydrogen atom, then it's going to be simply 1 proton. So that's why in many cases, in many videos, you'll see hydrogen ion being referred to as proton. Now, our chemical reaction is balanced.